on 7th. But I think that's next week. But I think that let's choose not too soon. But I want because I will also teach other classes there. It would be easier for me to administer the cuts on the same day, so we can have the cuts towards the end of November. Yeah, but for the purposes of this class, this is the last topic. We will continue to have the classes. If you have any questions to make clear, but for all intents and purposes, after this class, you already know what you need to know for the entire class. So the last part, in fact, is analysis of statically indeterminate structures by direct stiffness method. The same idea, except now for the first excuse me, for trusses, we don't have moments, we only have direct forces. So just to go slowly to establish some working principles, I will after this demonstrate using an Excel sheet. Is easier. Hopefully you can excuse me, you can follow what is done on the Excel sheet, and if you have a question, please feel free to ask. So after this chapter, you should be able to derive stiffness and metrics for a truss member, define local and global coordinate system, the same thing we did for the frame, transform displacement from local coordinate system to global coordinate system, transform member stiffness matrix from local to global, the same thing we've done. Assemble member stiffness matrices to obtain the global stiffness matrix. Analyze plane truss by direct stiffness matrix method. This is what we have done before as well. So an introduction to the stiffness method was given. I think we have done this. So no need to read a lot of stories, but start here. Plane trusses are made up of short thin members interconnected at hinges. So I think you should already know this from the first course of structures. The joints cannot be any other thing except hinges. That means they transfer vertical and horizontal forces that cannot take any moments. Okay, a hinge connection can transmit forces from one member to another member, but not moment. I think that's just repeating what I've said. For analysis purposes, the truss is loaded at the joints. Hence, a truss member is subjected to axial forces, and the forces remain constant along the length of the member. The forces in the member at its two ends must be of the same magnitude, but act in opposite directions. I think this is just reminding you of what you should already know. If someone is talking, if you have a question, please raise it. Ibrahim? Okay, so this is what you are saying. So there's a constant force. One force is in the opposite direction to the other. So excuse me. Now consider truss member having cross-section area A. Actually, this is a repeat of what you probably have done in mechanics of structures, but to lay out in detail probably it will enhance the understanding. Now consider a truss member having cross section A, Young's modulus of E, and length L. Let the member be subjected to axial tensile force F as shown under the action of constant axial force F applied to each end, and the member gets elongated by unit length U as shown. So this idea should be fairly straightforward. Elongation may be calculated using this equation. This is from Hooke's law. You know that the force is directly proportional to the elongation. The constant of proportionality is E, right? So if you manipulate the equation, you find the force as AE over L. This should be very familiar. Remember the stiffness matrix related to axial stiffness is AE over L. You've done this. Now just trying to explain ahead what you see. Now the stiffness matrix is in fact the force that is required to cause a unit displacement. That's why for the axial displacement, the stiffness matrix is for the axial direction is A over L. I think you should be pretty familiar with that. So in other words, the stiffness matrix in fact for force is a force that can cause a unit displacement. For moment is a moment that can cause a unit rotation. For torsion is amount of torque that can cause a unit shear strain. That's it. But here we are talking about only shear stresses. So F is Ku. All right. Now K, you shouldn't be surprised, is this, and the U is a unit when you're talking about axial stiffness. So defined as force required for unit deformation. I think I already said this. The so the above relation 20. Please, if you don't understand, if you have a question, you can stop me to explain. The above relation is shown in the equation is true along the centroidal axis of the truss member. Now this is the detail. Is around the neutral axis. Of course, you know the variation of shear stress. If you deviate of the centroidal axis, probably there might be some difference. But in reality, there are many truss members in a truss. For example, consider a planar stress shown in 24.3. For each member of the truss, we could write one equation F is Ku along its centroidal direction, which is local coordinate system. Each member has different excuse me local coordinate system. To analyze the planar truss shown in figure 24.3, it is required to write a force displacement relation for the complete truss in coordinate system common to all members. Such coordinate system is referred to as global coordinate system. So the idea is that the each of those uh, each of those each of those members have separate orientations, just like for the portal frame. So the orientations, if you consider each individual orientation, uh, is different from the universal orientation of each member. So you need to convert the orientation into one global reference coordinate system, because each of the members have different orientations to the horizontal.
Now, if you consider each, then it might be confusing. So you instead you need to consider the orientation, one global coordinate system for the entire, to represent the entire truss. So we talk a little bit about the local and global coordinate system. So loads and displacements are vector quantities, hence a proper coordinate system is required to specify their correct sense of direction. Consider a planar truss shown in figure 224.4. In this truss, each node is identified by a number.
Hello.
Yes?
Can you like this, please?
Sorry? Is it large enough?
Yeah, yeah.
Okay, so the consider planar truss in 24.4. In this truss, each node is identified by a number, and each member is identified by a number enclosed in a circle. The displacement and loads acting on the truss are defined with respect to global coordinate system XYZ. The same coordinate system is used to define each of the loads and displacements of all loads. In a global coordinate system, each number of planar truss can have, I think the spelling of planar is wrong there, but this is PDF. Let's see if we can edit it. No, that's not. Edit is where here. Planar, where is that? Same code to define is lost. Planar here. No, it's you can see it. It's okay. So loads in truss, each node is identified by a number. The displacement and loads acting on truss are defined with respect to global coordinate system. The same coordinate system is defined. So displacement of all loads in global coordinate system, each node of planar. So this is the issue. This was the problem. The planar truss have only two displacements, along x-axis and another y-axis. So uh, for the for those just joining, please register your attendance on the chat. The registration the registration number and name. Now, because we are saying trust members can only transfer forces in x and y direction, the displacements can also be only in the x and y direction, nothing else, because we don't have moments, we cannot have rotations. The truss shown in figure has 8 displacements. Each displacement is a degree of freedom. In truss is shown by a number in the figure at the joint. The direction of the displacement shown by an arrow at the node. However, out of these 8 displacement, 5 are known. The displacement indicated by numbers 6, 7, 8 are 0 due to support conditions. The displacements denoted by the numbers 1 to 5 are known as unconstrained degrees of freedom of the truss. Displacements noted by 6, 8 concentrate degrees of freedom. In this course, a known displacement noted by lower numbers and the known displacement noted by higher numbers. Anyway, here I'm just trying to the same idea like the portal frame, but I chose to use maybe this explanation maybe will enhance your understanding, but it's the same idea. The these numbers denote the degrees of freedom, what we said before. Now, for me, this numbering system is confusing. I'll demonstrate to you with an example and give you the notes. So you will. The most important thing is to understand the concept rather than these are some nitty gritty details. The numbering is confusing because if you start by 1, 1, 2, 3, 4, okay, and you see 4 is here, it's quite confusing. You can have different numbering system like okay, 1, 2, 3, 4, consistently 5, 6, 7, 8. The numbering in such a confused way, but this is their system. But please make sure the point is not lost in the uh, in the in this system. I'll show you exactly what to do. The same. I will show you two examples. One for trust, and the one we did last week. There is an Excel sheet which I will show you. Of course, I will show you the Excel sheet, but I won't send you the Excel sheet because students tend to be lazy when they are spoon fed. Instead, I'm recording this and upload. So if you will want some references, you will be forced. You will be forced to go to my channel and watch. But the point is, you need to understand the concept of what happens. To analyze the trust shown in 24.4. So here you can see this is in 90. For example, member number 4 is 90 degrees. All right, and member number 2 is 270, right? Now one of the member number 6 is some angle 45, not 45%, but 135 probably, and this is a 45. Number 5 is 45. So you can see these have different orientations. So local coordinate system is when you consider now each individual orientation. Now, but for global system, you have to assume all of them have the same reference coordinate system. That's the issue, and this should be quite clear with the example we did before. Now, to analyze the truss shown, the structural stiffness matrix K need to be evaluated for the given truss. So the stiffness matrix at the global must consider the universal orientation or with a common reference axis system. This may be achieved by suitably adding all the member stiffness matrices, what we've done before, which is used to express the force displacement relation of the member in local coordinate system. Since all members are oriented in different directions, it is required to transform member displacement and forces from the local coordinate system to the global coordinate system so that a global load displacement relation may be written. And all this is you need to know the load condition. Also, you need to know the support system will tell you somehow the which displacements are zero, which ones are not zero. All right, and this is building up from the basic knowledge of structures that you should have you have garnered, I think, from structures part 1, 2, and 3. So here consider so 24 point. We need to see the diagram first. So this is the diagram, and I tried to use this note to lay out in detail so that it's quite clear what we're talking about. And in any case you don't understand anything, you can read and have a quite clear ideas of what we are talking about. So because navigating this seems difficult, we save. I have to close and open it again. Open with yeah, so here, so consider a member shown in local coordinate system xy, x prime, y prime. The loads are applied along the centroidal axis. Only possible displacements will be in x prime axis and y prime axis. Let u1 prime and u2 prime be displacements of the truss member in local coordinate system, i.e. along x prime axis. Here subscript 1 refers to the node of the truss member, subscript 2 refers to the node of the truss member. Excuse me. Give displacement u prime 1 at node 1 and the member in the positive x prime direction, keeping all other displacements to 0. This displacement in turn induces a compressive force of magnitude EA over L. Remember, we say the force is EA over L. If U is 1, then the stiffness matrix is EA over L. So in the member, thus the force now, okay, and the force in the direction 2 is equal and opposite, right? Negative as it acts on the negative direction. Similarly, and this is condition is for equilibrium. Similarly, by giving positive displacement u2 at each end, the tensile member, tensile of magnitude EA, inducing the member, so q1 prime and q2 prime. Now the forces developed at the ends of the member when both displacements are imposed in nodes 1 and 2 respectively may be obtained by the method of superposition. So maybe we try another with diagrams, probably make it a little clearer. So here, and also I told you when you're talking about the this of issues, you induce the displacement one at a time. So if this is the member, this is the coordinate, so this is the positive y and this is positive x, so y prime x prime, right? Then ignoring the y direction, you induce a unit displacement. Okay, let's call it u, but assume it's a unit displacement. So we said that the stiffness matrix is EA over L, so to get the force is EA over L times the displacement. Now you should not be surprised that in this direction the displacement is the same, but is opposite, as so that we have equilibrium. All right. Now if you are to do the same here, apply a unit displacement here u2, the q would be the force would be the stiffness times the displacement. Of course, for equilibrium purposes, there will be an equal and opposite force in this direction as well. So that's for the x direction. So now the to get the force, superposition means you add. So the so you add because based on the references and the direction. So the P1 prime would be the E A over L times U prime 1. This is positive, and the second one is negative. Of course, with a different displacement, and U are the same. P2 would be, of course, the reverse of this from what you've seen. So if you are to, so we can proceed to write this in terms of the displacement, in terms of the so force. Remember we said force is K times U. Now in the portal frame we said force is K times U plus the fixed ended displacement, but this is in the local axis system. I don't know how I can. Okay, let me go to PowerPoint. Probably it's easier to explain. PowerPoint. Please, these equations are important. You should have them at your fingertips. So here, remember you can ask, so stop me anytime if something is not clear. So we said that the force, okay, they are called P now. Okay, let's just use the notations. P is K. This is the stiffness matrix times U. But remember, this is when we don't have any orientation. We are talking plus fixed ended moments or fixed ended forces. But this one, no orientation. So this is probably for a beam. Is okay. But for other members that have orientations, then this is K is the transformation matrix, the transpose, or the transformation matrix times K times T, of course, times U, plus the fixed ended moment. So for these ones that have some orientation, you have to change. All right. But unfortunately for trusses, for truss members, then this is just that the K. Now this K is the one that has already been transformed times U, because we cannot have any fixed end forces in trusses because we load them at the joints. For beams, we have fixed end forces because the loading is usually between the joints, the nodes. But in trusses, the loading are at the nodes, so the forces are just the K times the displacement. So this is the idea. So if you want to get, this is the force matrix, the stiffness matrix times the displacement matrix, which can be summarized as equation 24.6. So this is just to demonstrate to you. So this is what can be referred to as the K. All right, but I think this is too simplistic to, but it helps, of course, to develop the idea. And so this is the so you remember what you are doing. This is node 1, 2, and node 1, 2. So the stiffness for 1, 2, and 1, 2. If you are talking about more members, 1, 2, 3, 4, 1, 2, 3, 4, 5, and the displacement matrix will also grow big, the force matrix as well. So now that's for the local. So how do you transform the local to the coordinate system? More or less what we talked about previously. So a truss member is shown in local and global coordinate system figure 24.6. 24.6 shown there. Let xy prime y prime z prime be local coordinate system and xy z be a global coordinate system. Yes, so this is the this is the local coordinate system, and this is the global coordinate system. So how do you do this? The nodes of truss member be identified by 1, 2. So let u prime and u2 be the displacement of nodes 1, 2 in local coordinate system. In global coordinate system, each node has 2 degrees of freedom. Let me try to demonstrate here. Please, you can ask questions. This is the local member coordinate system. There are 2 degrees of freedom because the forces can be transferred along the length or vertically. So 2 degrees of freedom, we can move in direction x and in direction y, and 2 degrees of freedom at both ends. So in the first, here we can have movement here and here, those are 2, and then at this end we can also have movement here and there, so those are 2 degrees of freedom. Alright, so let u1, u2 be the displacement of nodes 1 and 2 in local coordinate system. In local coordinate system. In global coordinate system, in each of these nodes has 2 degrees of freedom, u1, v1. So in the so this is the local coordinate system, and the global coordinate system. So in the global coordinate system, the movements are v1 and u1 and u2, v2. So this is one, and the other end u2, v2, and the nodal displacements at node 1 and 2 respectively along x and y direction. Let the truss member be inclined at an axis theta as shown in figure. It is observed from the figure that u1 prime is equal to the projection of u1 on x axis plane plus projection of v1 on x axis, thus 24.7. I'll show you this later, how the transformation occurs. So here we simply have to, okay, maybe we see the transformation first. So this is just trigonometry. Excuse me, to make sure you can understand what's happening. So if you move in this direction, all right, but these this is the actual orientation on the horizontal direction, but this movement is in reference to the local axis. So if you have to convert this movement into the global, into the common frame of reference. So this becomes u1 cos theta, and this becomes v prime sin theta, and the same can be done on the other edge. In any case, this is just geometry, trigonometry based on geometry. So therefore u1 prime is u1 cos theta plus b1 sin theta. Then u2 is the same idea but a little bit reverse, u2 cos theta plus v2 sin theta. So this is how to write the transformation matrix. So the transformation matrix, so u1, u2, the displacement matrix, the transformation matrix, and the displacement matrix. Please note, they try to simplify it here. I don't know whether this is a simplification, but I prefer you remember the L and M. I think is much more confusing makes more sense if you know what these things are. Cos theta, sin theta. Alright, so please, well, if you can remember here, but I really doubt that this is any simplification. This makes more sense to me. Okay, let me make sure I'm not losing anyone. Is there a question, class rep? Class rep? Silence means that there's perfection, or what? Or people are lost beyond comprehension. Class rep? Class rep? Hello? What does silence mean? You understand everything? Caroline? Caroline, someone? Hello?
Hello.
Yeah, everything is okay?
Yeah.
Okay. So the assurance is good. So we move on. So then, so let the the coordinates 1 be x1 y1, coordinate 2 x2 y2. Then the length, of course, cos theta is x2 over x1. That's no, I think this is the part I'm saying I don't like, because I don't really think the L and M is much of a simplification. It serves to, I think, well, if you can remember this, but as far as I'm concerned, this is much more useful than the L and M. But you can check it out if you think that makes more sense to you. Then the force transformation matrix, let P1, P2, P3 in truss members node 1, 2, respectively, producing displacement U1 prime, U2 prime in the local coordinate system, and P1, P2, P3, P4 before in the global coordinate system nodes 1 and 2 respectively. Displacements U1, V1 and V2. Refer to figure 24.9a to D, this one. Alright, so referring to figure 24.9c, this, so P1, of course, in the x direction, is it the x, there's a cos, in the y direction there's a sine. Similarly, P3, and at the end of the day you can construct a matrix in this direction. So here you have to transform the forces and the displacements. Okay, this is just to show you how to arrive at the final solution. But this is the journey. At the end of the day, I think you only need to know how the final result looks like, and you need to note here that this is a this is a transpose of what we have talked about here. So here we were transforming the displacement, here we are transforming the forces. So you need to note that that is a transpose of this. So the forces and the displacement, you can see the relationships between the, okay. So these are transpose. So if to get the force matrix, transpose matrix times the so this is the force, this is the force in the global direction, is the transpose of the transformation matrix times the force in the local direction. So this is kind of showing you the relationship between the local axis system and the universal, the global axis system. So here the displacement in the local axis system is the transformation matrix times the displacement in the global axis system. So this is the relationship between the displacement in the local axis system and also in the global axis system. Okay, so having done that, that's why I did not want you to get surprised when we get to the local the overall result. So here from equation this so this is the force in the local member is the stiffness matrix, the local member stiffness matrix times the displacement in the local member stiffness in the local member displacement. So we substitute from the equations we have talked about here before. So but this uh, uh, the yeah, so but what is the relationship here between these relationships here is already known, so we can substitute. This is the local member, so if we put the global direction, the transformation matrix times the stiffness in the stiffness in the local member times the displacement in the local member. Again, that's not all. If you want because normally you need the displacement in the global direction, not so I want you to note how this equation is developed. This the local member, this is the reference this equation is from the local member only. So local member forces is the stiffness, local member stiffness times the local displacement in the local member axis reference system. Okay, now but we refer to the global, the more often than not you need a global axis system. So to do this, the transpose of the transformation matrix times the local member stiffness, but still we are referring to the local member displacement, which is not what we need. Okay, so to do that is and this is the beauty is it goes back to what we talked about before. So this is the force in the global uh, direction times the transformation transpose of the transformation stiffness. So the local member times the transformation matrix and the displacement in the global direction. So this is okay, and then the force times the stiffness. Force equals the stiffness matrix. The force matrix is the stiffness matrix times the displacement matrix. Now what we should remember is this is how to transform the stiffness matrix to the global direction. That's all. Now, from equation 2.147 represents member load stiffness in relation to the global coordinates, and that's where we wanted to go. So this is it. So K, this is how to get K, all right? And then you transform based on the transformation matrix and the transpose of the transformation matrix and the transformation matrix. So what all you need to remember is this. The way we remember EA over L, 6 EI over 12, 12 EI over L cubed, 6 EI over L squared, the same idea. So this is how to get the K prime in whatever orientation. That's all you need to know. So this is like the stiffness matrix. This is like the stiffness. No, not the sorry. Yeah, the stiffness matrix actually. So I won't go into the details, but this is the most important thing that we are getting ourselves into. So, but you can see the stiffness. All what has brought all this is the issues of the transformation. So, in fact, this here in is the transformation matrix. This is the transformation matrix. All right, and this makes it the stiffness matrix. So from here, I'm going to demonstrate with an example to make it clear. Unless there's a question or someone needs clarification. What's happening? And that will make it very simple. So here, just substitute there the first row, first column, second column. So this 1, 2, corresponding to 1, 2, 3, 4, 5, and 6. So degrees of freedom. So you just substitute there. And for the fourth member, the second member, because these 3 and 4 overlap, 2 of them. So 3, 4, 5, 6, 3, 4, 5, 6, and of course EA over L. So the length is 5, EA over 5. Please take care of the places that overlap. So let me remove this. So that's what I have highlighted. All right. So at least I need someone to confirm that is once you remember this formula, there's nothing difficult really. A class rep or anyone else. And if you don't understand anything, you can ask. Brian. No, some of these people who said these things are difficult, that's what I want to see. There was this some lady here kept Faith, please confirm that once you remember this formula, just a question of substitution, and the rest, at least if you can derive this and that, the rest is fairly straightforward. I'm still going to show you, but at least I need you to confirm that you can get this and get that. And actually you can see the figures there. You can confirm with your very calculator there, just to see that we are not doing anything magical. Anyone please confirm? Okay, now I am giving you a chance. Please confirm, just to inspire confidence in you. For member 1, confirm that you can get the values for column 1. Some 2 minutes, just to inspire your confidence, to show you that it's not very difficult as you might imagine. At least you should have confirmed at least the first value. Anyone else who can confirm? Now I need someone just to confirm that they can derive the values for the first, at least the first column. Class rep. Or anyone else? People are so quiet, I'm wondering what's happening. Class rep. Even the class rep is quiet. Faith Wangari. You know you have to respond, because otherwise I don't know how to help you.
Which I assure is very simple. I don't know if there's any other easier way to say. So only key is to memorize this. Now, once that is done, so this you can see here to make the global stiffness matrix. So this one you have already multiplied times TT times all those things. So you only need to remember that. And actually for trusses this is always the same. So you don't need to remember anything else. Then once you do that, you can see here, because there is no overlap here, this is 1 to 4. You just copy. Okay, maybe now let me show you. You can pay attention. So I can delete these ones just to make sure you understand the point. So let's see here. I delete this. I clear. Okay, let me clear everything. So for this part here, up to 4 equals this. So once you do that, okay, I'm also showing you the Excel skills, because these are 4 by 2. So you highlight 4 by 2, then you say equals to, but because you are highlighting a lot of things, you control and shift, you press them together, and you put something is wrong, you put enter. Anyway, let me redo it again. Clear. So you highlight 4 by 2 the same. Now I think maybe you should highlight when pressing no, okay, you highlight that, and then you control put equals to, then highlight this, then you control press and shift, control shift, you press them together and put enter, and it copies. Alright, now for these ones are 0, you highlight enter equals 0, control shift and enter everything. You can see that this part is equal to that, so control you highlight, Control Shift Enter. This part would be 0. Equals 0. Control Shift Enter. Then this part is equal to this one. Sorry, this one equals Control Shift Enter, and this part equals this part. Control Shift Enter. And this part is the part you add, so equals this plus no, something is wrong. Control Z equals this plus, okay, this. Then you Control Shift and Enter. Alright. Is there any question how to combine the same thing we were doing with the portal frame? The only thing I can say is tedious if you're doing it manual. You can see how Excel makes it easy. So even if you had 4 members, the only thing, each one of these members contribute 4x4 matrix. If you have 3 members, or it will just be a long matrix, but you can see it's very simple, and the root is this. So anyone with any question, because the only thing is, once the first thing after, if you remember this, then I think your work is half done. And then the other issue is just to combine, which as I have demonstrated, should fairly be quite easy. Please record your attendance. Record your attendance. Please don't misunderstand me. Maridi is saying some things that I did not say. All I said is in radians because of the Excel, the material I'm using, alright? It doesn't have to be radians. Degrees can be expressed in radians or in degrees. But the Excel, the tool I'm using to demonstrate this, is set to work in radians. You could change the setting in degrees just the way you can change in your calculator. That's the point. I think that should be very clear. So someone please confirm that you know how to get to where we are. So this is the local member stiffness matrix for number 1, local member stiffness for number 2. These are the nodes 1, 2, 3, 4, 5, and this is how to get a global stiffness matrix. Also, don't forget the EA over L. Anyone, please, I need you to confirm that at least the point is understood. Masi Wanyonyi, please confirm that the point is understood. No, just any Excel, this guy. No, the Excel, any Excel, as long as you know and you can write the formulas, any Excel can be done. There's no specific Excel. Excel is an Excel. Just ordinary Excel sheet should be able to do this. Of course, you have to know how to manipulate. I think I've already shown you how to do that. I need someone to, if there's a question, class rep. Class rep. some response from you guys that the point is understood. If there's a question you ask. Yes.
Yes, okay.
Yeah, you understand. Okay, fine. At least that assurance. So once you combine and you don't forget the what you are taught, so I have to go back and remind you. So this one I have to remind you. That we said that the first matrix P is equal to the stiffness matrix K times the displacement matrix U. For usually is plus the fixed end forces, but for truss this is 0 because the loads are at the loads are at the node, so you don't have fixed end forces. So once you do that, so this is the P matrix, the K matrix, the U matrix. Normally, ordinarily, you don't know these things, but so this one now reminds you, now requires you to remember what you have studied in the previous courses. So this is a pin joint. Pin cannot take any moment. In any case, trusses, when we are talking about trusses, there are no moments. So we can only talk about the force in the movement in the x direction, U1 and U2. But because this is a pin joint, unless you are told that it's allowed to move by assumption or universal agreement, a pin cannot accept any kind of movement, so U1 and U2 are 0, isn't it? Yes?
Yeah.
Then U3, this carries load by movement, so if it is not supported, it can move, so this one cannot be 0. U3 and U4 cannot be 0. Again, at the support, U5 and U6, because of the nature of the support, they are zeros. Right? That's first point. Q1, Q2, we don't know because the supports have to have some values, so we don't know. We leave them alone. Q5 and Q6 also supports, but at least we know Q3, Q4 because this the trusses are loaded at the nodes. There's nowhere else. So if they are loaded at the nodes, those forces have to be the same. So in the x direction, horizontal direction, the value is 5. In the vertical direction, there's nothing, so it's 0. So like I've told you, if you are to multiply this, this will give you everything 0. But this cannot solve anything because we don't know U3 and U4. So we go where we can solve. So that will eliminate the first 2, 3. So 3, 4. That will only leave us with 3, 4 because 3, 4 we have 5 equals this times 0 plus this times 0 plus this times this U3, 4. So you can see here. No, is that 3, 4? Okay, let's see. Okay, yeah, that's okay. So plus this times this plus this times that. The rest of those things are 0. So you end up with this and that. And the fourth one, we only concentrate on this because we have these values here and we can solve. The rest of this we don't know. This we don't know that, so we can't do anything about this. So you only concentrate on these ones with some values here, the same way we did for the trusses. Actually, I will also demonstrate for the truss. My interest is that you really understand what is happening. So you concentrate on this, and the beauty is these parts are 0, and the The first two are 0, the second two are 0, because if you multiply this, anything by 0 is 0, so you only remain with this, which you can solve. Now remember, this was EA over L, so then these highlighted ones have to be divided by 5. So 1.5 divided by 5, you can see 0.3, and this divided by 5, so you don't forget that. Alright, now if you solve, okay, now that I have taken the difficult work of trying to demonstrate to you, this one you can, this is a 2 by 2 matrix which you can solve, I think, very easily, but because I am showing you how to do it in Excel, so this would be the inverse of this times that. Alright, so how to solve inverse of this times that? So I try to demonstrate to you. Okay, the formula is shown here. Those who are interested, you can see. This is, and some of these things, in fact, actually you can some of these things you can, after this, if you take some minutes on YouTube to see how to solve, should be very easy. So this is a 2 by 2 matrix times 1 by 2 by 1. Why is it 1 by 2 matrix? Will give you 1. Is it 1 by 2? 2 by 1, 2 by 2, 1 by 2. Okay, 1 by 2 matrix. So you highlight those who are interested. Okay, this is not part of the course, but this is just to show you how to solve. But I'm worried because when I show you this in exam, you have to calculate manually. But this is 2 by 2 matrix, so it should be easy to solve. So you use what is called M-multi. You are multiplying two matrices. The first matrix is the inverse of this, the inverse of that. So M inverse, these functions are in Excel. M inverse of what? M inverse of this. So that is the first thing. So this is the first matrix that you're multiplying. Then you separate them by a comma. You multiply by that. Okay, should be enough. Yeah, you can see when I put the comma, when I put the bracket, please notice what happens. So you can always tell you when the, so that means you can see this bracket encloses, this one becomes bold to show you the extent. Okay, you can see something is also wrong there. So you have to after you do that, you have to shift, control shift, press them all together. I did not press them all together. You can see it solved only one, which is not right. So equals M-multi. So this is an opportunity for you again. M-multi of M inverse. M inverse is to get the inverse of this matrix. I think that should also be okay, and then control, yes. So that gives you the solution. So U3 is this, of course, over EA, and we don't know what EA is, so it's okay, because that EA is a constant, so it's okay. So that's it, and you can substitute back here what these values are, and then you can solve everything for yourself. So I will just show you. So let's isolate this down here. Let's isolate this down here. But this is EA over L, but L is 5, so because you want to use it to solve, you must substitute. So here you can, okay, let me demonstrate to you. So let's clear everything. So this equals all this over 5, control shift and enter. Okay, now so this matrix times this will give you all the forces that you need. I mean, it's that simple. So if you want to prove that, because this was already done, I show you again. So this one equals this matrix. No, that's not. And not, you have to always multiply matrices using a mult. So this is the first array and comma, the second array, comma, control shift, enter, your answers. Now this is the solution. You can compare your solutions to what you need. You can see it's very simple. Of course, this one they use their method and I use mine. You can see there's no difference. The principle is the same. Of course, this mine gives you a bigger picture. You can see you can solve the in here, the values here, but here they are only concentrating on the reactions alone. But in any case, I prefer the fact that you can look at the big picture. At each node you can get, because that's the function of the stiffness matrix method, that you can assemble one matrix, stiffness matrix, that can solve the reactions at any node, no matter the fact that they are supports or not. So you can see the values are very close. This not closely exact. That these people have ignored this part, the unsupported part, but you can see the values are more or less the same. So unless there is a question, and hopefully I hope that I have demonstrated that apart from it being tedious, it is in fact learning. But now the rest of the responsibility is on you, in fact, to do a lot of exercises. I will go out of my way to demonstrate. So I will send you this. In fact, I should send it now. No, I will send you later. I can send to you now. And I need us to go through the example we did yesterday, in the previous week. There's an Excel that makes it. And I forgot. So there's that, and there's this part here. There is the Excel is done for the truss. So let's try the. So I'm gonna show you how to do the portal frame. The one we did last week. So the one we did last week is here. So first of all you need to know here so if it were a beam, for a beam, this one and this one and this one and this one, the rows and columns for the axial stresses will not be there. So beam will be a 4x4 matrix. So that you should know, 4x4 matrix, because the axial beams are not designed don't carry zero axial forces per se, but the ratio of the shear forces to the axial forces. So the axial forces are quite minimal, very very small, to the extent that we can assume they don't carry any axial forces. Now for this one, because it's slanted, of course, you have to be concerned by because of this orientation. It's a factor base because beams are horizontal. Once you load, once you give it normal forces, there is zero chance that there is an axial force. There is a force in the axial direction. Okay, but so this is because the beams are perfectly horizontal. But beams that have some orientation, whether 90 or say any other angle apart from zero, of course, because of that orientation, there will be some axial force either way. So please note that difference. So for beams that are horizontal, this matrix reduces to 4 by 4. The axial portions are not there. So that's the first thing I have to say. And the second thing is just to try to solve this. We tried it last week, and it proved tedious but not difficult. Anyone saying difficult, I think that is a very wrong characterization. So again here, because these are beams, the moment part is there. So this is 1, 2, 3, and 1 is 1, 2, and the moment part 3. And then 4, 4, 5, and the moment 6. And the same idea with the part BC. So AB, the one with the issues is part AB, which you need to think about. So and then the stiffness matrix is just that. So the first part is just to write the lengths, the fixed forces, and try to arrange the matrix as already shown. So if you want to see E over L, and actually you don't need a lot of things. Once you solve the first 3, the rest of these have some relationship, so you can just say equals to, very easy. The same thing even with the truss. So once you solve the first 3 columns, these ones have some relationship with the other one, and to check whether you are correct, please always check the symmetry. It's important. So you can always catch yourself when you're about to make a mistake or when you're making a mistake. It's easy. That's why I like structures, because it's pretty easy. So once you substitute here, of course, remember you can always ask a question if required. So and then, so the transformation matrix is always sine cos theta, sine theta, negative sine theta, cos theta, and 0, 0, 1. The rest is the same. So this is the transformation matrix. Alright, should be easy. So once you get the transformation matrix, now let me remove this one. Yes, so and then let me also remove this one. To make it easy. So just demonstrate, and then hopefully you understand what you should do. So this is the transformation local member, then the transformation matrix, cos theta, sin theta, negative sin theta, cos theta, 0, 0, 1, and then you can produce the rest. Then you transform the first one. I've gotten myself into it, let me just try to demonstrate. My only point is I hope you are learning something and not assuming that is difficult. So this is equal to n moles. I'll remember, okay, I have to also remind you this. What we are trying to do there is this. The principle. This is how people write programs, by the way. You should know this. So what we are trying to do there is also the principle has to be sound so that whatever you're writing has to make sense. So what we are trying to do is the stiffness matrix is the transformation of the local. This one we already know times there. This is what we are doing. Okay. So now m moles, we are multiplying three matrices, the TT, so m moles of m moles because you have to make the transpose. So transpose. If you don't understand this, I think you shouldn't worry too much. Understanding what it means is more important. So we are multiplying the transpose of this times the local member, the untransformed local member matrix. So this m mod will multiply. So once you multiply this and multiply that, you get the result. And then now we multiply with the transformation matrix and you control shift and enter, right? So that's the only difficult part. The rest, this is just the E over L and direct, because this has no orientation. I mean, this is 0 degrees, so this is fine. And then the numbering 1, 2, 3, 4, 5, 1, 6, 1, 4, 2 up to 9. Then the rest is just to combine. I think I've already demonstrated this part for 2. 2. So this one you copy, this one you copy, this part you copy, this part you copy, and this overlapping part you have to add. And I've also highlighted this is from number 1. This is from number 1, and this is from number 2. Okay. Then once you arrange the matrix in that manner, you bring this here just to make some sense. Yeah, someone has a question? A question? Okay. So you bring this here. This is the force. So this is the first one is the horizontal force, vertical force, the moment. That's node 1. Horizontal force, vertical force, moment, node 2. Horizontal force, vertical force, moment, node 3. And of course the associated displacement, movement in the horizontal direction, the movement in vertical direction, and then displacement, and not displacement, rotation, and so on and so forth. Now from the boundary condition, of course you know that this is a fixed joint, so all these have to be 0. again at C it to be fixed, this have to be 0, you know that. Now this one is not supported, so those ones can have value, U4, U5 and U6 can have values, alright. U4, U5 and U6 can have values, that's okay. Now the forces also, this P1, 2, 3 can have any value, so that's okay, but 4, 5, 6 have to be 0 because we're talking about equilibrium. Q7, 8 and 9 also have values. So again what we said before, so that will make us only concentrate on 4, 5, 6. Alright, so that is also a 3 by 3 matrix which you should be able to solve. Of course with some effort. There is a Gaussian elimination should help you to solve this, or if you have a good calculator, or for now for class exercise you can use Excel. So then again you isolate the 3 by 3 matrix because this part, even if you multiply it should be 0, and this part if you multiply it should be 0, so that's why you concentrate on this, only this. So you concentrate like this, and so this is what that means. Of course this, so this one was, but to solve, so the P matrix is the K matrix times the U matrix plus the fixed end forces, alright, so don't forget. Alright, so the fixed end forces, where is that diagram? It's, yeah, I'm using it. The fixed end forces, please make sure you talk about the direction as well. So this one, the fixed end forces are 0 on AB, fixed end forces on BC are the vertical. If you put it at a simply supported beam, the VB and VC are the same, which is 9, 9. But please remember that the moments have a direction. So you can assume, in this case I'm assuming MBC is positive and MCB is negative. You can assume the reverse, but please remember, if you do that consistently, there should also be no problem. So please don't forget that in the exam, the direction, the moments have to have opposing direction for equilibrium. So this is why you can see, so this is the K, so this is the P matrix, the P matrix, the K matrix, the U displacement matrix, this is the fixed end moment. So now to be able to solve, yeah, so you can see everything is 9, the horizontal direction has nothing, the vertical and the moments are 9, 9, and this the horizontal has nothing, and the fixed values here. So for the moment in the other direction has to be negative. I hope that is clear. So now to be able to solve, you also have to consider, so if these parts are 0, if you bring these values here, you can see now they're negative, so that you're able to solve. And to get these values, okay, I got myself into this, so maybe I have to finish it. Clear, but this is not part of the class anyway. We're supposed to be taught how to solve. Of course that's now maths, but anyway, so this is M multi of M inverse of this, of that, times these values there, Control Shift, and those are your answers. Now if you copy the matrix again, the same idea here, so you copy the matrix here. So this what, previously one student asked a question So you see at this point, if you put something at the outside the bracket, please remember, because you can easily forget that. So but here there was nothing outside the bracket, so you just copy. So once you copy, then the rest you know are zero. The ones these ones you just copy. The ones you have solved here, and these ones you have solved there, you just copy. Don't forget the fixed odd moments. And the rest I think is just a question of mathematics. So if you want to see how these values come about, I'll just demonstrate to you. So these are the reactions from 1 to reactions from node 1 to 1, 2, 3, from node 1 node 1 to node 3. So to see, so equals n nodes m equals m moles of this times this plus, and then something is wrong, plus m moles of this, sorry, of this and moles plus all this should be okay. Something's wrong. Something probably is wrong with the something is wrong, in fact. So I have to do it again. The formulation, something is wrong. Escape here. M moles. So if you highlight Excel is smart, it will tell if probably you highlight like 6 by 6 and then when you pick 5 by 5 it will not agree. That's the issue. Control Alt Shift. Yeah, so these are your values, and just to check, of course we doing BMD and all those other things you already know. We can see, we check the first, these values we said would be 0 0 here, here 0 0 0. Of course we are doing some estimations. You can see the resultant value has very low, so it's close to 0, 7.22 negative 16, close to 0. But most importantly, in the horizontal direction 9.15, you can see 9.15. Incidentally, okay, these are my values, these are the values from the reference, just to show you that once you do the correct thing, you have nothing to worry about. The answers are quite similar, if not the same. So 6.75, you can see 6.75, 0.5, you can see 0.499, 0.5, the same. Of course here the 0 0, so you can see here 9.15, 9 point positive, you can see 9.149, 1.5. Here 11.25, 11.25, negative 14.69, negative 14.7. So everyone is happy, and I hope that demonstrates you is quite simple and clear. It should be clear, and of course when you understand what you're doing, I think you can see that things are quite simple. So unless there's a question, the class ends there. I believe I have done my part. If you have a question, you can try the exercises. If you do have a question at any point, the class rep can reach out to me and we can arrange. So you study the cut will be